To simulate a massive biological system, like a solvated lipid bilayer at the atomic level, we must calculate the trajectory of every individual atom. In standard Class 1 and Class 2 all-atom models, the computational cost to do this scales at big O of n squared. Every nucleus must be evaluated pairwise against every other nucleus within the cutoff radius. Because of this steep nonlinear scaling, even the most powerful supercomputers hit a bottleneck. Our view of the simulation gets trapped in the microsecond timescale, leaving slower macroscopic phenomena, like phase transformations, completely invisible. To actually observe the complex biology of the mesoscale, we simply have to abandon the exact representation of individual atoms. This requirement introduces the coarse-grained paradigm. Instead of tracking exact atomic coordinates, we group multiple atoms together into a single mathematical interaction center known as a bead. By combining molecular components, like mapping a terminal methyl and a methylene bridge into one site, we drastically reduce the system's degrees of freedom. This chart shows the thermodynamic consequence. By removing atoms, we mathematically smooth out local minima in the free energy landscape. With these fine-grained barriers erased, we remove the enthalpic friction that naturally slows down atomic motion. The dynamic timeline artificially accelerates. But these newly created beads are non-physical abstractions. They do not exist in nature. Because of this, we cannot use standard atomic force fields to govern their behavior. We must derive entirely new empirical potentials. We trade true physical reality for the massive computational capacity needed to observe complex, emergent, mesoscale biological behaviors. Take a specific molecular pairing to see how this reduction works in practice: 2 interacting benzene rings. To model just these 2 rings in an all-atom framework, the simulation must calculate 144 individual site-site Lennard-Jones interactions. We apply a coarse-grained reduction, collapsing each 12-atom ring into a single, centralized Lennard-Jones site. Those 144 calculation pathways reduce to a single interaction vector. That single remaining mathematical vector must now accurately approximate the net thermodynamic and structural behavior of the 144 discarded interactions. This introduces the central parameterization challenge. How do we assign accurate forces to a particle that does not actually exist? The predictive power of any coarse-grained model relies entirely on the mathematical rigor used to define this singular interaction parameter. One approach is bottom-up force field development. This extracts coarse-grained parameters directly from a high-resolution reference all-atom simulation. This relies heavily on force matching. The forces acting on the newly defined beads are mathematically fitted to match the ensemble averaged forces acting on those exact same atoms in the detailed atomistic run. This chart maps the target metric for structural accuracy, the radial distribution function, or RDF. We derive the ideal target curve from the atomistic data, but as you can see, our initial coarse-grained attempt is severely mismatched. To fix this, we apply iterative Boltzmann inversion. We determine a potential of mean force from the target RDF, then use a recursive mathematical formula to update the coarse-grained pair potential. The simulation is run repeatedly. With each cycle, the mismatched curve iteratively shifts and bends until it perfectly aligns with the target atomistic RDF. Bottom-up methods guarantee that our abstract beads structurally replicate the specific spatial geometries of the original atoms. The alternative is top-down parameterization, an approach that bypasses atomic-level reference simulations entirely. Rooted in chemical engineering, this method derives parameters by fitting them directly to macroscopic experimental data. This flowchart details the statistical associating fluid theory, or SAFT. We start with macroscopic inputs like density and heat of vaporization and feed them into the SAFT equations. The equations of state process that experimental data to determine the physical size, the collision diameter, and the attractive strength, the well depth, of our beads. Leading models, such as Martini, often use a hybrid of these 2 philosophies. They combine bottom-up structural data for bonded interactions with top-down thermodynamic partitioning for non-bonded interactions. Top-down parameterization ensures macroscopic thermodynamic accuracy, even if the underlying interaction models are entirely artificial. Knowing exactly when to deploy these respective models is crucial. An all-atom model is strictly mandatory under specific physical conditions. If your system requires capturing precise quantum effects, charge transfer, or specific hydrogen bonding geometries, you must use an all-atom model. It is also required when analyzing exact entropic and enthalpic barriers during small molecule ligand point mutations. Coarse-grained models become the necessary standard when we scale up to observe collective, long-range orientational order over massive length scales. They are ideal for tracking phenomena like lipid membrane self-assembly, membrane surface undulations, or massive phase transformations. The choice between models is dictated by identifying which length and timescales govern the system's core behavior. But stripping away atomic resolution introduces a severe thermodynamic limitation known as the representability problem. This graph tracks the paradox. Because integrating out degrees of freedom removes intramolecular terms from the virial expression, a single model cannot perfectly reproduce both structure and pressure simultaneously. Optimize for structure, and your pressure accuracy falls apart. This is coupled with the transferability problem. A parameter set explicitly optimized at 300 Kelvin will produce highly unphysical data if you attempt to run that exact same system at 320 Kelvin. A coarse-grained parameter set is a highly localized abstraction. It is inherently incomplete and invalid outside of its specific thermodynamic state point. Because of these paradoxes, a researcher cannot blindly trust the output trajectory of a coarse-grained simulation. Rigorous validation is mandatory. First, we must verify the system's kinetic energy distribution. This check confirms that the applied thermostat is actually sampling the correct canonical ensemble. This terminal displays the results of testing the time-step dependence of energy conservation. A failed integrator test, highlighted here, indicates a Hamiltonian drift. This test detects long-term integrator drift, an instability frequently caused by the mathematically smoothed potentials used in coarse-grained models. We must also check for unphysical coefficients of thermal expansion across temperature gradients, and we monitor bulk density over extremely long timescales to ensure the system hasn't slowly collapsed upon itself. Coarse-graining is a profound mathematical tool, but only relentless thermodynamic validation ensures that it reveals the truth of biological systems rather than inventing it.